Okay, so today we have the agenda smart cameras for 1 and 2D solutions. The overview about the next 2 hours. The first step will be a short intro to EVT, what we are, where we are located, and what we are doing. So the next step will be what hardware smart cameras would be available for 1 and 2D smart camera solutions. Then a short intro to the EyeVision software with the real EyeVision software. So if you have any questions, simply feel free to ask. After that, we will have a short view to all the tools. And based on that, we will do our first demo programs. And based on that, also some examples to show that it's really easy to make also solutions for 1 and 2D smart cameras. So what is EVT? So we are in Karlsruhe, it's in the south of Germany. And we sell our distributors or a subsidiary. We have one in Korea.
Ihr Anruf wird gehalten. Bitte warten Sie einen Moment. Please hold the line.
And therefore, yes. So you can buy it either directly if you're in Europe or for the rest of the world. At all these locations, you can buy over our distributors. Finally, of course, if you want to see this, I record all the complete webinar. That means you can find it after words in our YouTube channel to recapitulate everything if you missed something. So we are located in Germany. We have 2 locations, one in the Gartenstraße. This is our headquarters with the training and support center. And the second one was our main development close to the University of Karlsruhe, KIT. As I told you, we sell over directly from Germany to German Europe companies or worldwide through distributors or integrators, or of course OEM customers. Our key product is the EyeVision software. That means we try to run the software on all kind of hardware platforms. One of these are the so-called smart cameras, or maybe also vision sensors, or we could also say embedded systems, whatever it means. We will have a look to it in the next few minutes. So what kind of products do we sell? So we sell this product for standard PC or 686 or some other CPUs on Windows or Linux. Therefore, you can buy the package, the different packages, which makes it easier to do the solutions, especially for we are able to tailor-made our software, means we add or reduce the tool set, which optimizes the price for example, quantity applications. So we have 1 and 2D, and for, of course, standard systems, we have also 3D instruction set. We will have a short look later if we have a look to our 3D smart camera also. And of course, we also support thermal cameras, and for that thermal instruction set to do all kind of thermal vision, not only measuring temperature, also find voids and cracks in different materials. Today we have a look to the, let's say, EyeCheck or EyeSense systems, which means these are the smart cameras with, and if you look upwards, with the standard 1 and 2D instruction set, depending on the camera. That means if you use a smart camera, you get a standard application, a standard instruction set which fits to the smart camera or the vision sensor. And but as I told you before, we have one software which runs on all platforms, which makes it easier to make a solution if you know the software from the PC side. You will see even the programming of a smart platform will be very similar. Finally, we have a deep learning tool set which enables you to use deep learning also on with our software, and of course, depending on the hardware platform, also on smart cameras. Here, a short overview of the EyeVision software, which looks like for the standard interface. And on the left side, you see these smart cameras, only a choice. We will have a closer look in a few minutes to it. And also the other cameras from 3D, thermal, hypervision, and so on for the PC or embedded systems. The software is available or localized for German, of course. We are Germans, but we also have English, French, Spanish, Turkish, Russian, Chinese, Mandarin, Korean, and Japanese. You simply select the language and you get the user interface in your desired language. Today we use English. We have an English webinar today, so we use the English version of the software. The customer markets are nearly everywhere where machine vision can be used, from semiconductor, automotive, electronic, pharmaceutical, food, beverage, rubber, wood, and many more. Why? Because the tools for machine vision doesn't care about the market. You use the same measuring tools to measure semiconductors, or if you measure pins, or if you measure the gap in ignition system, or measure something else, it's always the same. So there is no restriction in the markets. What we have done, of course, is to create some specialized instruction set for some of the market to make it easier to do the solutions in these markets, like semiconductor, for example. Of course, normally we exhibit on different exhibitions, and this year, also last year, we are not so sure which exhibitions will happen. We exhibited on some, that's so-called virtual exhibitions, but we hope at least the Vision Show in Stuttgart and maybe the ITE show in Yokohama will take place and we can be physically there. So this was the first short overview about the EyeVision software. So let's have a closer look to our today's main theme called Solutions with Smart Cameras in 1 or 2D. And therefore we go to our second presentation. The first step will be now to have a look to all the smart cameras which are available and can be used for the solutions. Then a short intro to light and lens. Of course, for smart camera, it's more important. It's light and lens is always one very important part of a machine vision solution, and this fits also for smart cameras, especially because the reduced computational power in smart cameras needs a better light because it reduces the number of tools to optimize the image. At the end, it's always valid. A good signal is the best part to do a good measurement, and this fits also to machine vision. Then we will have a short look into the EyeVision software structure, the different capture process options for capturing, which is similar to the standard capturing with a PC. Of course, the difference is the smart camera. Then we do some combination of data which we capture, and we do some evaluations on images. So before we start with the hardware, if you start the embedded or remote control software of the EyeVision version, it looks like this. It's similar to the standard version for all who know it. For all who don't know it, they will see, or they have to have a look at it, and you will see the main difference is this a small tool in the front, which you can see in the front. It's called device configuration, which allows you to connect to a device like a smart camera and do the operations, do the programming on the smart camera. So first, let's have a look to the hardware. Therefore, I have a short presentation for the smart camera hardware. We subsidiarize it in SmartCameras. So I said at the very beginning, what is the difference? What is the difference between a smart camera and an embedded system? Well, in my opinion, there is no big difference. Maybe there's a housing around it, but you will see it in a few minutes. So for smart cameras, we support x86 based smart cameras. For these smart cameras, you can of course run Windows or Linux on it. If it's an ARM-based smart camera, we suggest, or we support only Linux. And of course, we do the separation, or between, let's say, smart camera and vision sensor. What is the difference? From nowadays, there is normally no hardware difference, because it makes no sense to make a special slow hardware. The major difference is the amount of software which is built in the smart camera. And finally, if you have a look to the EyeVision software, to reduce the instruction set is very easy, as I told you, for which we can do also for some other reasons. So we have these vision sensors based on the same hardware platforms than the smart cameras. And for smart cameras, we have the standard EyeVision software version, which has a full instruction set, and therefore we call it smart camera. Both, as you can maybe remember, the two orange entries in the list are brought to the market with two different names. We name it iSense, which means vision sensor, that means reduced instruction set, or iCheck with the standard instruction set of the EyeVision software. So that's the main difference. To have a closer look to the embedded systems, what in our opinion are also smart cameras, we have a look to these, and finally show you that the idea that there is no big difference between a smart camera and embedded system is very small. So the first step is, let's have a look to the different manufacturers and the smart cameras, which you can simply select and use the remote system, and therefore build a smart camera solution. So we have these x86 based smart cameras, which can simply be bought from the market or over us. And if we sell it as a bundle, we name it iCheck, AdLink, for example, and then you get this smart camera combined with the EyeVision software. So therefore, you see these different x86 based smart cameras. All these are either available with Linux or Windows. And furthermore, which one is a better or the not so good camera? It's difficult at the end. One have to decide, what do I need, for example, how much computational power, what is the right solution which I need? Does the manufacturer have the solution for this smart camera? This is a major difference to a standard system. You buy the smart camera as a fixed combination of sensor and computational power. So if you use a standard system, you can connect any camera to it and select the resolution. For smart cameras, you have to select the smart camera, for example, based on the sensor which you need, for example, if the manufacturer has this kind of smart camera. So you can simply go through all these manufacturers, select the choice you need, and then you can use it. The same fits to the ARM-based systems. So this is more the kind of smart camera which is a standard nowadays. And also here we have different manufacturers which we support with our software, which enables you to do different solutions. And so maybe it's interesting, you saw it also in the x86 based smart cameras. You get it with light and lens, and because the CPUs have less TDP, the housings are much smaller than the Intel-based or x86-based smart cameras. So you can select from smaller housings which fit to your needs. Which manufacturer is the best is another question. Maybe the housing size is a good option to select the right smart camera. Here, for example, this yellow one on the top is 20 by 20 by 40 millimeters. So it's a very small smart camera if you need a very small one. And so of course, you don't get every smart camera with every resolution. Either you select it based on the resolution you need or based on the size you need. The combination. So there is the basic choice. At the end, the programming is always the same. Or if you say, okay, I have an endless material like woven or non-woven stuff, you need a line scan smart camera. Right now, we support the Jupiter L series. This is a hardware which is built by ourselves, because on the lack in the market to have a line scan camera. Of course, some of the manufacturers of the smart cameras recommend to use an area scan camera and do a readout of one line only from the sensor. But even if you use this, the total speed of this one line is not doesn't reach the line speed of a real line scan camera. So because there was no on the market, we built this smart camera. And of course, the EyeVision software runs in it. So this is a standard other area scan camera, or which we support. So as you can see, we roughly have more than 20 smart cameras supported, and we still work on the support for more. Beside of this, you are always able, because the smart camera is, if you have a look to it, it's the CPU and the sensor and I/O capabilities in one housing. In most cases, you don't have a connection for a keyboard or mouse. So we also name it headless systems. So that's why we have this so-called remote system, which we have a closer look, which allows us to use the same software and program it. And for the programming, we use PC or embedded system, which allows to be connected a mouse, tastature, and display. So let's have a short look also to the embedded systems. Maybe you don't find the right smart camera on top and you want to build your own smart camera, then you could use also size-wise these ready-made boards from different manufacturers. These are all in the size of a check card of so it's mostly 55 by 85 millimeters, very small. And because these are standard components, if you compare it with the other CPU speeds in the smart cameras, these are mostly also much faster. Which one is the best? It's difficult to say. Most of these have also USB 3 and GigE interfaces, or for example, like the Raspberry Pi 3 and 4, and also some of the others, they have a MIPI interface, which allows you to connect directly a sensor module to this board. And if you build this in one package, it looks very similar. If we have a look, if we go back to maybe this one or this one, it looks very similar to these smart cameras. Of course, there is no housing, so maybe you have to build your own housing, or you have to build anyway the complete machine, and you can attach very close to this CPU unit the housing, and then you can also use this one. Based on the standardization of the MIPI interface, you have an option of a lot of different sensor modules from 640 by 480 to 13 megapixel with either CS mount or C mount or with no mount. You have a real wide choice of sensors related to the smart cameras, which normally have only really limited choice of sensors. Finally, of course, because these are standard components, you have real interesting price section. I think everybody who knows the Raspberry Pi, it's about roughly at 35 or 40 euros for the computational hardware. And if we compare it with 1.5 gigahertz to all these others, it's also very fast with a quad-core CPU. Right now, for the moment, you find only dual-core CPUs in the smart cameras with an ARM or quad-core in the PC area. But anyway, at the end, with a much higher price. So this is only an option to build your smart camera based on your own. We also support these Nvidia boards, so especially if you run the deep learning, the Nvidia platform is very good. But we also support some deep learning accelerators to run these on embedded systems very fast. So these are, of course, PC boxes, which can also be programmed like these smart camera above. That's why I have these here. Of course, this is a PC. You can program it as all PCs, but you can do it also based on the remote system like a smart camera. So as you do it with an ARM-based system. And as I mentioned it before, of course, today we have a look to 1 and 2D, but of course there's also a 3D smart camera. It's called Saturn. This has also dual-core Cortex-9 CPU inside, and it's a triangulation-based 3D sensor which can operate independently, so that you have also the option to make 3D solutions with the EyeVision software. Or the other option is the thermal smart camera to make smart thermal solutions with the same software. And now what's coming up, you will find very soon here in the list LUCID time-of-flight smart camera, which is time-of-flight sensor built time-of-flight sensor with an ARM CPU, dual-core ARM CPU, where you can run the EyeVision software also inside. And to round this hardware section up, and because I told you before what is the difference between a smart camera and let's say an embedded board. If you have a closer look to these embedded boards, you will see here, for example, these Raspberry Pi Zero connected to one of the MIPI sensor modules. So, of course, you don't have a finished housing, but if you simply add here a small housing, you have a nice 8 megapixel or any MIPI sensor which you connect to this CPU, you have a nice, very compact and, let's say, cheap smart camera. The same here is a Raspberry Pi 4 with also this whatever 8 megapixel or 12 megapixel sensor, or with a lower resolution, of course. And therefore you get also finished housings, either mostly here with these MIPI standard lenses, but you get, as you see it here, also with the C-mount or CS mount lens, which enables you to have an immediately very powerful smart camera. This was only a small, short intro to this option. Of course, everybody have to think about it if this is usable in industry, but it's a good thing to think about it, especially the compute modules of the Raspberry Pi Foundation have a long delivery, have a long term delivery, means they guarantee for the next 6 to 8 years to deliver this module, which fits to what we recognized the last roughly 10 years or so. While from beginning with the first Raspberry Pi to the current one, you still get all the old ones, or because they are compatible, you simply can use a new one. And with the EyeVision software, of course, you don't see a difference. You see only the difference in speed. This was only to round the hardware section up. And now I would go to the main part to make smart camera solution in 1 or 2D. The main part is, of course, we have this hardware. Without software, the hardware doesn't do anything. Independently, if you use one of the standard smart camera hardware platforms, which I mentioned before, or if you use one of the embedded systems and build your own smart camera or embedded system, what you really need is something to program it. Of course, as always, you can program it in C++. It takes time, and it's also a pain to do this, especially if it's an embedded system. And therefore, we ported our EyeVision software into these smart camera platforms to allow you the standard interface to program it. And simply to distinguish between vision sensor and smart camera, once again, the difference is if you buy a vision sensor, you use any of the hardware which I mentioned before, and we add simply maybe only the matching tool, which we have a look to it later, or we only add the code reading tool, and so on. And then you have the vision sensor for matching, for robot vision, for code reading. Or you use the smart camera with the full instruction set for 1 and 2D. Then you have the same instruction, then you have all these instructions right away available, and you can do a combination. And of course, you can always add tools to the vision sensor version to allow the vision sensor to do more than the one for what it is sold. So you can start with the code reading vision sensor and add maybe the measuring tools, and then it's no problem simply to do also additionally measuring or something else. And of course, all the other remote devices. If you use one of these remote devices, as mentioned before, you can either use the built-in MIPI interface, or you use any of the GigE or USB cameras which are available on the market to select the right sensor solution for your task. Therefore, which hardware you want to use for these smart devices or smart camera, it's on your side. So we had this already. So what is the real difference between the EyeVision software? I mentioned it before. You have this device configuration tool, and then you have this the camera viewer as you have it always. As long as you're not connected, you see there is no connection to a smart device or smart camera, and you cannot access it. To make it more, to have a better feeling for this, I would simply start the EyeVision software. So we use the remote version of the EyeVision software, and we have a look to the first steps, how we handle any of these smart cameras. So of course, as always, we start the EyeVision software normally at the very beginning. That's why we need some time here. It searches the network for available smart devices, and after it's done, we arrive here on this point. You see here, if you know the EyeVision software, on the left side, the instruction set, in the center, the program editor, and here the camera viewer. And so it looks very similar to our standard EyeVision software, because it's the EyeVision software and there is no real difference. The difference is, in this case, the software, the user interface runs on a PC or even on any embedded system. So that means you can also use, for example, a Raspberry Pi, because it has a monitor and mouse connection, and run the remote system there and do a programming of a smart camera from a Raspberry Pi, or program another Raspberry Pi from this Raspberry Pi. So for what is the real difference from our point of view? In the embedded systems, we run a runtime system only, and we connect from the remote system to that runtime system. And the protocol between both allows us to do the programming remotely. So how we do this? We simply select the device configuration, and here we see in our company network, of course, I have different runtimes running. For example, here on the sensor part cameras. And for today, to do the demo, I simply use a runtime which runs on my PC. This is much easier to demonstrate you how it works. At the end, we have this special version of the EyeVision which runs without user interface on the target platform. After we selected the right one, in this case we use the smart device, we press connect, and then we see, in this case, the system tries to connect to the smart camera and says, okay, the smart camera is not running. If you have a real smart camera, normally it starts up when it gets power. If you have a runtime running in your PC, you simply should start the runtime. So this is powering up your embedded device. In this case, we powered it up, and then once again we can connect it, and after a second you see here everything is green and the smart device is running. So in this case, we get also information about the smart device. So if it's, for example, a sensor part camera or one of the others, or it's a Jupiter line scan camera, you see the information about this. In this case, the information is, it's a local process. It runs on a second core or on any core of the built-in CPU, and does its work. So, for example, now it captures an image, and this smart device captures the image, and the image data, as well as the I/O and all the other communication, is transported to the programming environment. This here is a programming environment. And you can also do tests with this system. So it also allows you the 90-minute test for these remote systems. For example, if you don't have a smart camera, but you want to see how it works, you could use any second PC you have anywhere around, and you install the remote system on that PC, and then you can control from your programming PC this remote PC. That's what I mentioned when I said what is the difference between a normal system and a remote device. The remote device normally has no video output or some other stuff. Most of the smart cameras which we had a look to it have Ethernet, some PLC IOs, and that's it. So that's why they are called smart cameras. They are reduced to do their job. For many of them have also RS-232, but that's it. How they are built. No PC, no nothing. Simply put it to the position where you want to do the operation, and you get simply the results. Of course, if you program it, you need the information from there. So you have to display what the camera sees. That's why we have this remote interface, and we can see the image data as well as the IO lines. And if you have an RS-232, also you see the results of the RS-232 communication on the programming front-end user interface. And that's exactly what we see here. So in our case, for example, the runtime runs on this PC, but you can run this runtime either on any other PC, like let's say Raspberry Pi, or you run it on one of these smart cameras. It's exactly the same. For the software, there's no difference. This remote device has an option to capture an image and to do whatever you want to do on this device. The really important thing at the end is that you also get the real speed of your target system. So as I told you when we walked through the hardware, these smart cameras are built once, and they have to last for a while. That means if you have a look to the available smart cameras on the market, say run something between 800 megahertz to, let's say, maximum 1.5 gigahertz. This is what smart cameras are today. So, and they are not based on the latest technology. Mostly they are, if it's ARM, they are from maybe an A9 version, or maybe they are an Atom from the early 5 years ago, when Intel started with the Atoms, or slightly after that. So to have a feeling if your solution works on the smart camera, you can simply have a look to the timing at the end and see if you are as fast as your process needs it. From our experience, most of the processes, or let's say if you do the standard gray and color image evaluation, up to 10 parts per second can be done with smart cameras, depending on the instructions that you need. Of course, if you need area-based instruction set, it takes more time on the target system because this needs massive computational power, and then you see the lag in the CPU speed of these systems. So let's have another look here. So we saw this in reality, how to connect to one of these smart devices, and we can do then from there the image capturing. Smart devices, so let's have a look to it. In this case, the smart device is one instance here on this PC, or if it's a NASA system, you have to connect to the NASA system. That's one of the reasons why I simply used it here, because we can have a look in this smart device because it's on the same PC. So the smart device has the same structure as we have it in the rest of our software. And so if we have a look to the project file, we see here all the information, and you saw here we don't use images from a camera, we use it from a file. We have here these training files, and that's what we are running on it. So if you want to simulate something else, the good thing is now if you're on the same PC, either you have a camera connected, then you can capture it also on the camera. So today we could go to our main projects, and for example, we want to do some maybe color examples later. So we can simply say, okay, we need some color images. Okay, that's not so many. Anyway, we take these color images, and we can simply go to our embedded device and projects, and simply store these images here in the embedded device so that we can use it. Of course, if you have a normal embedded device, you can also connect the camera, or the camera is connected if you have a smart camera, and you can, instead of capturing from a file, you use capturing from a camera. In this case, so I made this demo, this small program with capture image. Cyclic means load each time the program is executed, load one image. Let's say if we want to, you want to capture now the color images. Either if you have a camera connected, you can use it from the camera, or as we have done it now, we simply can say, okay, we want to use this stored images there. And now if we run it again, we get these color images. So there, for your programming, there is no difference if you program it on the same device where you are working, or if it's simply remote controlled. The images are captured from the connected sensor at the remote device, or you can, for example, you can also store in the remote device from your sensor the images and work after you finished with these stored images. This is one of the, let's say, advantages of this remote programming. As you can see here, for the device configuration, we have these sync from camera and sync to camera. That means if we do some programming, of course, it's synchronized from here to the remote device and vice versa. So if you run the smart camera and you store on the smart camera maybe all error images, you simply can sync it back to your programming environment. Then you can run your process and you have all the images to do the optimization of the program on your programming tool. And if you finished, you can sync it back with the corrected or the optimized program into the camera without stopping the process, so that you have a simple option to easily do this optimization of the smart camera without being connected or permanently to the smart camera. And yes, so we had already a look to our instruction set. We have the 1D and 2D instruction set, which belongs to everything what is here 1 and 2D, and of course 1 and 2D in gray and color. And of course, depending on the target device, you could also use deep learning. In principle, the recognition, the non-training part of the deep learning software runs also on the bare metal CPU. Depending on the CPU, it takes more time. So we recommend to use a hardware which supports also this evaluation in deep learning, like, for example, an Nvidia board, or maybe the hardware where, for example, the Intel Myriad is built in, which makes it much faster if you have these speed improvements based on the hardware. So what I mentioned at the very beginning, and I simply want to focus it only for a few minutes or a few, not very short time, is, of course, there is no difference between a smart camera or a normal PC-based solution. Light and lens filter is really important and is half of a stable solution, and especially because the smart camera doesn't have these high-speed CPUs. It makes totally, or it helps a lot if you optimize the image quality. If maybe on a PC you can use some filters to optimize your image, but at the end, optimizing images is the second best solution. Optimizing it with a digital filter operator. The best way to optimize images is always to have the right lens, the right filter, and the right light. If you have this, you can also make stable and fast applications on smart cameras. Of course, I said they're running with 800 megahertz or maximum 1.5 gigahertz, but by heart, this is not slow. Let's say roughly 10 years ago, or let's say 12 years ago, there was still machine vision, and the PC ran at 800 megahertz or 1 gigahertz, and we did a lot of machine vision. That's why these smart cameras are not slow. And of course, it helps a lot if you optimize the contrast at the end. And optimizing the contrast means simply find the right light, filter, and lens. And then finally, if it's not possible, you can use also some additional digital filters or whatever. The final, what fits to all is good contrast is good, means good machine vision, bad contrast, bad machine vision. And this is still true. If you need more information about all the options in light and lens, I can recommend our webinar about light and lens, and of course filters, to have a better insight to the design of this light and lens. Yes, today we have this 2D gray and color and 1D line scan area, but as we saw, we also can operate on thermal images, and there are smart thermal cameras, and we have also a 3D smart camera which can operate as a smart camera without a PC. So let's start with some examples, and so we start maybe with our first demo. So we use this our standard training tool and simply make some solutions. As I told you, it's in principle you have all the options you have on the on a PC. The only difference is software runs in the remote device. So remote device fits best to all these different options like smart cameras, embedded system, or headless PC systems. The difference is you have the programming environment on one system and the execution unit on the other system. And of course, as you see it today, you can have also this execution system on the same PC. That means you can run multiple, let's say, smart or embedded devices on one PC, which are operate then as independent as a smart camera. Of course, the question is now, why using a smart camera? I don't know it. I think there is a market for smart cameras. Of course, nowadays, let's say way back in the early, in the early years of machine vision, not the early years, but in the first century when machine vision started, roughly in 1996, 7, 8, you had only this real big 19 sol systems, which goes in a cabinet, and it was difficult to integrate machine vision everywhere. At that time, really, the first smart camera goes back in 1996 or 7, 8, roughly in that time. When the first smart camera appears, it was the advantage here. You have a small housing with a sensor, with more or less fast CPU, but you didn't need the cabinet, and you didn't need all the infrastructure of the cabinet. You simply plugged in the camera, and the camera did some machine vision. If you look back to that time, at that time, the CPU was really limited, but it was still enough to do machine vision. If you have a look to the list, or if we recapitulate the list, we looked today with these different smart camera with an x86 or with an ARM inside or one of the embedded systems. All of these systems are much faster than the PCs or machine vision computers which are used at that time, and therefore there's no real need now, based on the CPU speed, to really say I need a smart camera. If you use a smart camera now, as I showed you, this Raspberry Pi or the ODROID or the Nvidia board, they are also very small, and you can connect any kind of camera to it. And if you don't want to have a programming environment at that display and some other stuff there, you simply can remote program it as you do it, of course. And therefore, when using a smart camera or an embedded system, it depends on, do you need a finished system in a housing, or don't you need it in a housing? If you don't, you can use one of these PCBs and integrate it in your machine. If you need a ready-made system, which you simply use the M12 connector and it runs, then a smart camera is the right solution. So it's difficult to say, okay, a smart camera has this or that advantage. It depends simply on what you want to do or what you have to do. We are very happy. If you have questions about the hardware which fits to your needs, we are happy to help you and give you some additional information, or find out with you together what might fit from all these hardware components. But at the end, it's a remote system which runs. So in many cases, you could use, for example, I don't want to say this is the only platform, but for example, the Raspberry Pi, and you use the USB 3 camera then you have the flexibility to have the right sensor, and you have anyway a very small but powerful system. And of course, with the remote programming, you don't need a display or anything else. You simply can program it this the way I show it to you here. Or the other thing is, if you have multiple cameras which you need on the same at the same position for different tasks, you could also use a small PC like a NUC, connect 4 or whatever USB 3 cameras to it, and make your hardware and you have independent running programs on it. So you program it anyway with the remote system, but everything is on one PC. What the best solution is, I can't tell you. It was only a short intro to the option why using smart cameras. It depends on what you need. So at the end, you have here also some options for debugging stuff, especially also for firmware update. Of course, if you have a remote device without a monitor and anything, sometimes we have new versions of the EyeVision software, and therefore we have all the infrastructure here to simply update the runtime on this embedded device without being an expert of programming Linux, which is mostly the operating system on these devices, and how to do it. You simply can do it with a button click from this position. The same is if you buy a license for this embedded device and you need more instructions, we have this option to update it. So as I told you, you could run, you could buy a code reading tool with QR code reading, and a few days later you need maybe some measuring tools. You simply can update the license based on the license file, and it runs on and immediately you have all the tools in the target system. So let's have some closer look how to program a smart camera. I guess if you worked with the EyeVision software, you know we can use now all the tools we have depending on the license file. So let's say if you want to track the object, you could use either the blob tool and you program it exactly like it's on this system. You have exactly the same user interface with the same features, so you can of course highlight and select what do I want to select the white or the black parts. So if I select the white parts, we get these two white holes, additional the white the background, which is a border part. Sorry sorry, I should stop my microphone. Yes, sorry. So you simply select the color of the part or the object. Maybe you ignore it, you do a test and you see, okay, we have two objects. And if you run it now, so far we don't need this tool because we are connected and the connection stays alive until we disconnect. And now we have our first solution. The part is this tool searches the object, counts it, and determines the position of these parts. Or if we simply select the black one, we get also the information for the black one. And you see it's also fast. So this is exactly how we program it. There's no real difference to the normal EyeVision software. Wait a second. what's the real difference is, whenever we add here a tool, we don't add it here on this PC. We add everything on the remote device. That means whatever you see here is done over the connection, whatever connection it is. Normally it's an Ethernet connection, is done on the target system. And the program at the end is also on the target system, and it runs there. So therefore, we see here the time which is needed for the execution on the target system. Of course, the advantage is, if you see, oh, we are too slow here on the target system, you can simply save the program anyway and use it and connect another faster hardware to it, and simply add it to the and simply use this faster system, as far as there is one which fits in your system. So let's say find black, and now we have the find black tool here. So if we disconnect now, and then the system asks us if so should we save the current program? Should we also sync all data to our local project folder? So we had a look to the folder of the target system. This was this one here. We see it's the instance. In this case, the instance is the target system or the remote system on the same PC. So if it's the smart system, we couldn't go to the smart system, but in this case, we see here how the smart system looks like. And after we've done this, we can tell him, look, if we disconnect now, we want that the target system runs the application after we finished. And now we create a backup here on our system, and the target system runs now. So now we are disconnected, and of course the smart camera does the task which we have programmed now. So in the background, without seeing it, the target system is now operating. On the target system. Is now operating, and if you have a look at it, we see here the runtime takes 35% of one of our cores and runs in the background so we don't see anything because it's the remote system, but it simply runs in the background and does whatever we have. And therefore, we can also have multiple runtimes. So on the same system, they do it independently, or we have these different systems. So now we can reconnect to the system, and if we reconnect immediately, we get from the system the resulting values. And if you have, only to show it to you, if you have a look to the runtime exe, it nearly needs, here it is, we can run it a little bit, then it needs, so now, where we have it here, now the runtime is here. So you see here, when we start it, we need and if we stop it now, we see immediately the runtime now has 0% because we do not need CPU power. If I do this one, maybe I do it side by side and it doesn't disturb. Then we have these both options here. Then you see if I execute it, we need runtime, we need CPU power because we run the tool on our target hardware. Of course, the target hardware is here now in the same system, but we see it's really running. And this is one of the major advantages. So, and of course, independently, if you use the block tool or, for example, let's have a look. We use this matching tool. All the tools which we deliver with the smart camera works exactly like they are on the system here. So it's the same if we have a new pattern for the contour matching tool. So the pattern is now stored in the smart camera and it's also executed in the smart camera. It's not here. And if we run it now here, we see the pattern matching works also as well as it runs on our system. And if you use the same option as before with the, oops, if we run it here, immediately when we run it, the runtime takes more CPU usage. And we see here also the user interface display needs only 13% to update everything here. The real task is done in that CPU core, either on the PC or on the smart camera. And of course, if it's a smart camera, the speed here depends on the speed of the CPU in the smart camera. So let's simply go through some examples and see how it works, and to show you, okay, it works exactly as if you're on your PC. For example, if you want to do some measurement, for example, you can use any of these tools here. Because we do image capturing with different parts to simulate also moving parts, we have to follow the part with our batching. So you do it exactly like on the normal PC. You use the result, for example, of the matching tool, and you say, okay, we have an origin and orientation here, and we use this one from register 0 and 1. And of course, we can draw the axis to show you what it's doing here. You see, we move the coordinate system from the left top corner into the part, so that we know exactly where the part is, because the measuring is done in this case on the part, on the tray, whatever is moving. So of course you can also disable this overlay graphics as on the normal system. So you have the new coordinate system here, and you simply can add now, let's say, our easy measurement tool, for example, the caliper. It works exactly the way like it works on the PC. So now we have trained this measurement, and if we run it now, the measurement follows this tool. Or for example, if you want to do it based on an edge detection, so you could use, for example, either use the probe or the probe line. The difference is, so we can also save the stuff. The difference is only what the tool does. If you don't know it, you have also the option here to activate the help command. And of course, here you see the remote device control description, how it works. And if we, for example, use the probe line tool, we get immediately the information how it works. So the probe line tool is a combination of a multi-tool. So I use now here the probe line and show you what it does with the with using distinguished tools. So let's say first we want to determine the angle between here and here. So we use, or we use it from here to here, whatever. So here you see reset point list fit align least square method to the points. If we do a test, we get the best fitting line through this points. And so therefore, as you see, this tool follows also the path. And if you don't want to use this multi-tool, of course, we have this single tool workflow. So then in this case, you have also to reset the point list, and you have to use the rect probe. It looks similar to the other because both are rect probes. And in this case, so you place it here or wherever we want to do the measurement. I think we have this one, and then we take, this looks very nice, like non-90 degrees. So we use the points here from this probe here. And right now we see we don't get here the best fit line. In this case, we need the separated tool for the best fit line and do exactly the same. We do a best fit straight line. And as a result, we get the best fit line through these points. So, and finally, it makes sense to calculate the angle between both. So we simply say, okay, we calculate the angle between straight line 1 and straight line 2, and we press test, and we see it's 120 degrees. So, and now we have as a result these 120 degrees angle, and that's one of our measurement tasks for the first step. What I wanted to show you, of course, we have always different options, as so we try to make it easy. Sometimes it's helpful to have the separated tools, like we did it with these three tools, like instead of using this combined tool, because this combined tool has of course some restrictions. You have to have one position where you can determine the line. If you have multiple positions, then you could add after reset multiple of these rect probes to the program, and these rect probes are then collecting the points into the point register. So once again, it's exactly the same like if you do it with the standard version, where the GUI runs on the same PC and has a direct connection to the incoming image information. That means the advantage of between these tools is exactly the same, and there is no difference. The difference is only in this case, we program now the remote device, not here on this PC. It could be anywhere in a smart camera or wherever. In the other case, it's done on the same PC. So when we finished, we save the program, and at the end, of course, if the angle is correct, we could also add some output or so, and this kind of stuff. So to do this, of course, we have to add here our nominal value and maybe some tolerance values, which allows us then to have good or bad results. 120, let's see if we have these results here. It seems we are mostly the probe test. We are at roughly, let's say 121 plus minus 0.5 might be closer to what we measure here. And then we have, of course, sometimes, let's run it and see. Now we are always in the tolerance, so we have to make the tolerance smaller, whatever. Depending on that, you could set the output commands here. That's what most of the smart cameras have, besides the Ethernet connection. You simply can control the I/O lines. That means you can tell the system if the result was okay from the last command or from the total result. You can set the output to high, so it means good, and in all other cases the output should be 0. So either you start at the very beginning with set output 0 to low, and we use permanent mode. You could also do a rectangle output, and so the reset, we do it in all conditions. So at the end we set it to 0 at the very beginning, or to low, and here if it's good we set it to high. So this would be now for the moment the first smart program which runs on the smart camera. We simply could then say disconnect. Then the normal questions are, and you see we did the presets the last time. We have the same presets again. After we disconnected, the software is running, and we say okay. Then we also sync the program and everything to our system here. And after we finished, so now we are disconnected and the smart device is running on its own. And you see on the input and output what the result of the smart device is. You see here it's as before, it's running, and it takes the 32% of computational power so far. And of course, because it's we have this Ethernet, you could also send the resulting data to our system. In this case, we have to select find black, and we could also, if we need the resulting information on a connected system, we could send it out. First of all, we can send the images from the remote device to our system, and in this case, he uses the image memory 0 with all the overlays and sends it to us. Or we can provide it to a web server so that we can connect to our remote device and have a look to the image data and the resulting data directly over the web server. In this case, the receiver would also be our local loop address 1, and so we can receive now the image of the resulting data. Or if you're interested in not only a good bad result, you also need the real results, the real angle. You simply can add the value to a transfer. You can say here, for example, angle, and of course the angle is a value. So this is as we do it also on the standard system. So we add one value to our send string, and Of course, if we send it out, we want to have only the latest one. The first thing what we do is we do a reset to that string. And after we finished, either after transferring the image or whenever, you can say send the resulting data. Either you store it in the device, or if the camera has a serial adapter, you could send it to here COM port 1, or you also can send it to any UDP or TCP IP network, and you have it then on that network wherever it is. The same belongs to all the other options to communicate with devices over these, let's say, standard communication ports. So, of course, if you have this COM port here, then you select the serial adapter, serial interface. Maybe you have a Profinet anywhere, a Profinet PLC. You are free also to use the Profinet on this remote device. That means after you have programmed and you finished with programming, all the communication, the resulting values, you don't have to use the PLC I/O of the camera. You could also integrate the smart camera into a standard network. The options here are the same as on the EyeVision hardware, on the standard EyeVision. The difference is only that you have that the communication starts from the smart camera. So whatever you connect, as you can see, it's exactly the same settings as you have it on the standard EyeVision. If it's a Profinet or it's a Modbus or MQTT, you can send out the resulting data over one of these networks to your hosting system. So also here, there is no difference between the embedded system and the PC system. You are free to do exactly the same stuff on both sides. Finally, if you have done all of this, you simply can connect, and then we see here the speed. Also for debugging purposes, you have the single step option. So you have all these options for programming and debugging, which you have on the PC side, but in the embedded smart camera or in the embedded platform like a smart camera. I think those of you who try to program a smart camera by yourself, based on, let's say, C++ or any similar language which allows you to program in Linux, knows that it's not so easy to program and debug things on an embedded platform with no display connected or anything else. So, and especially if it's a little bit more complex stuff like this one here. So in this case, yeah, it's for you, you have all these nice high-level tools. And I'm sure if you try to make the same based on a plain programming language like C++, it will take you much more time, especially also to add some stuff here within the programming environment. So it's the same if you finished, only to give you the advantage of this programming package in embedded systems. You could, of course, you can have multiple of these programs, and you can change between these inspection programs on the smart device as you do it on the PC. But exactly the same if you say, oh, I have to measure this here, the diameter. You have, of course, it's no big advantage to do this. You simply use the tools which we have right here. And at the very beginning, we start, for example, with as we did it before with the reset point cloud, not point cloud, point list. This is a difficulty if you have 3D and you restart point list. You use, for example, a circle probe. So also there's a probe which generates a circle, or you use the circle probe, which simply probes. If you use the red one, it's the same like with this tool. In this case, we use the separated tools, which you have to add manually. So you simply place the tool wherever you want to measure it. You press the best test button and you see, okay, I don't find anything, because we want to have the inward direction. So we search from inward to outward to the center. And in this case, either we have to select the object color. So in this case, the object color would be bright, or we say, okay, we start from inward to outward. In that case, the object color is black. That means now we find the dots because we come from a white object and find a black one. It doesn't have to be, as you see, totally black. It works on gray values, even if this image shows you, looks like it's not a gray image, it's a real gray image. And if you finished, you can use, in this case, as you have to do it with the straight line tool, the best fit circle, which calculates the best fitting circle here inside. And as a result here, we have this diameter. And based on this, we can do some additional resulting operations. And so it's really easy to add and operate on tools. Also, to have everything under control. So of course you have the also for the circle tool and for all other tools, you have this description, but maybe more interesting is for all who doesn't have so big insight. You have these registers. Maybe you thought about, if you don't know the EyeVision software before, why do the software know all this? And so we use here the point list, and then if we do it a single step, then maybe it's clearer for you. So if you go through this, you have the matching tool, and the matching tool generates. In this case, we need another additional list. So you see here we have different other lists here. So we have this point lister. In this case, we use the point register, not the point list. In the point register, we see the center point and the orientation point. This is the center point is here at the bottom of the arrow, and the orientation point is here at the end of the arrow. This gives us a point and orientation to adjust the coordinate system, which we see here now. And each tool generates a lot of data, and the data are always placed on top. And for example, the next one is the straight line tool. So it generates a straight line. And if you have a look to the line register, then we see here, this is a definition of the straight line. You see the latest result is always on top, and it's also marked in red. So it's very easy to understand what the software is doing. In this case, you didn't saw all the steps. So for the next tool, here, to explain it how it works, we use this reset point list. And if you have a look to the point list here, you will see the point list is now invalid. And next we calculate the, we fill up the point list with new values. These are the values from this tool here. These are all the cumulated points. So, of course, if you want to have a look at it inside, you see here, not so clearly, but here are the points of this tool. We could deactivate the predecessor tools, and then it's easier to see it. And the next step here is, if you go once ahead, you will find on top of the line register, because this is the best fit line, a new value here. This is the best fit line which goes to these points. And that's how the tool works. So now the angle tool simply takes the top, let's say this line, and the last line which went on top, this is the one before, and calculates the angle, and the angle appears here in the value register. So you have always everything in view, and it's easy to debug things if they are not working as you expect, or it looks somewhat strange. And of course, if you do now the next step, so we edit the resulting data from the angle tool to our transfer register. And if you have a look to that, and it's called global string. You see it here in the bottom. We entered angle 1, 2. This was the name, what we want to have, and the number. So we simply could add the number, but as you remember, maybe he said, okay, we like to have angle, and then we add a value. That means this value to one string, which we can send out then here later to our target system. And of course, maybe it's good to have a separation and maybe also a space between it. And let's run it again. If you have a look to the bottom global string viewer, if you run it again to this position, now we see angle double point 123.12082, which simply gives you an overview what we send out next to over the UDP package, or which is transferred when we arrive at this point. We said, okay, we want to send the global string. That's global string viewer via the UDP network to this IP address. And therefore, we have sent it. So another example for transfer of data is, in the next case, the best fit circle. Now, of course, because it's a best fit circle, the number of values will increase immediately when we go through this. Now we have a lot of new numbers, and it's about 99. I think if you have a look to this one, we have restricted it to 99. Let's see here. Yes, we want not all points. If we have all points, it's 360. So we say 99 points equally distributed through this circle generates the best fit through this one. And you see it's really best fitting this circle. And at the end was the next tool. We simply calculated this circle and put the value, in this case, I think it's a radius. It depends on what we have selected. Yeah, the radius to this value register. Right now we are not calibrated, but I think once again, I know it's repeating always. Of course, you have these calibration tools here in the EyeVision software, and if you want to measure calibrated, you simply use the calibration tool to calibrate your field of view. So you can also do the distortion correction if you have not the best lens. Of course, depending on the smart camera, maybe you don't have a very good lens, so distortion correction for the lens might be really good. The tool is here. Of course, this is an area tool. You will see if you use it on a on a smart camera was not so much computational power. It's not the fastest, but it's still here and it works. If you have a good lens, you can use the simple calibration tool, which does the simple scaling factor calibration, and it fits, and then you get real world coordinates for that. This is at the end exactly the same if you want to do robot vision, for example. Of course, we have the robot instruction set to communicate with a robot, not only a universal robot, in principle, any kind of robot. Right now we have a list of robots which we support, but it's easy to adapt to other robots. You see, we have the hand-eye calibration, which allows you to do the calibration of the field of view with the camera calibration. And based on this camera calibration, you at the end you have the registration between the robot and the camera, and of course this works as well as it works on a normal PC. It works also on the smart camera. There is no difference from our point of view between the smart camera and the PC, as you saw now over all the demos, and of course you have also the instruction set. So there's whatever you want to do. If you want to do code reading or any kind of 2D other operations, like as I told you at the beginning, chip control. Therefore, we made some special tools to operate on semiconductor belongings. You have these tools right away here, also on the smart camera platform. And the programming is totally similar to the smart camera platform. Now I have another short interrupt. Sorry, I needed a short break. So based on this, you have exactly the same tool set as you see. The real difference is the connection to the remote device. After connecting, everything works similar to the PC. There is no difference for you with the programming, and therefore you have the full functionality on your hands. All the communication, all the synchronization between the smart camera or remote device and the programming environment is supported here from this remote device console, which simply gives you the power to do remote device programming without knowing much about the remote device, what operating system runs there, how the operating system runs, and so on. And yes, I mentioned at the very beginning, okay, we want to have also a short look maybe to do some color processing. We could also do some code reading, but I think you could imagine there's no difference. You simply need, you need of course some images, or you point the camera to wherever you have some code which you have to read, either if it's a barcode, QR code, DMC code, or an OCR code. As you can see, also our latest development, the new OCR, is still here on the smart devices, as well as our standard OCR tool is available on the smart devices. And as I told you, we have these advanced deep learning package here in the meanwhile, which enables you to do, for example, also more deep learning solutions. So one would be also a very powerful code reading, OCR code reading tool, which enables you to do also difficult code reading. I simply recommend, and this is something which I also want to mention, of course, you don't have the project structure here, which you normally have on the PC version. We don't have the project structure here because in this case, the projects, and here you see the projects from the normal system, these projects are in that case the smart devices, smart cameras, embedded system, or whatever. But to have the examples, what you can do with for example, deep learning, but also with all the 2D examples for calibration, measurement, matching, bin picking in 2D, and so on, you simply should download these examples. These examples run also on your embedded device. So there is no, you can use all these examples to simply have an idea how to make the solution for your new task. That's why we made these projects. Of course, we didn't make the projects additionally for the smart devices because I know I mentioned it several times today. At the end, we have, because it's the same software which runs in the embedded devices, it allows you simply to test these on your PC, and you can simply copy over the program from these examples and use it on the smart device so that you don't have to start by scratch based on the smart device at the end. So yes, that's what I want to mention because many people think they have to start from zero. A short view into the list. I could also start, of course, maybe if you download the software with the download link, you get both. You get the EyeVision. This is the one which runs on the target system, maybe like the PC, or the remote interface, which runs on the remote system like the smart camera. So with this download link, you have also the option to download all these demos for the different solutions. So if you want to see how to make these solutions, it's the easiest way. You download, you use the download link for 2D area examples, and then you can simply say, what do I want to do, like a number plate reading or a crosshair might be really nice for an embedded system, or you want to see how to do matching or how to distinguish between touching elements, coil inspection, and so on. Or if you want to do how to do calibration, you simply go to measure and calibration, and you see examples, you see images, examples, and programs which shows you exactly how it works. And you can take it immediately to your embedded device. In that case, you simply go to your, however you name it, as you remember. We named our device here, which runs here on the same PC. We named it Smart Device, and you simply can store the program or all the image data which you want to have on the smart device. You simply go to Smart Device and you go to programs, for example. Then you see here the program which you made here. Also, you can simply add it to here, and after you edit here, you can simply sync it to the camera, and then it's transferred from here to the camera, and you can operate it on the camera immediately. So that it's very easy for you to simply test everything also on your smart embedded device, or you run it first on your PC with the standard version, and you see, okay, that's what I need, and then you simply sync it to your smart device. This is simply something which you should have in your back brain. If you have any questions, simply feel free to contact me, and I can help you then. As I mentioned, we have these also the 3D smart device based on our Saturn sensor, which is a smart 3D camera, which can operate on point clouds. As well, of course, you can use this Saturn also to operate on intensity images. And intensity image is similar to this to the gray image you see here. It gives you the intensity at the laser point. In some cases it helps, or you can also run the Saturn, if you run it as a smart camera, with the depth image. So you have really all the three options inside of the Saturn if you want to use that as a smart camera. And of course you program it exactly the same way. You only have the Saturn here then as a symbol, and you get the image information from that sensor. Or like for the thermal camera, you have also options to operate on thermal images from here, from pattern matching to measurement, to temperature measurement. That's exactly the same, because we have this remote runtime on the target platform, in that case on the thermal camera, and it runs there. And as I mentioned, the upcoming smart camera, time-of-flight smart camera from LUCID, has also a Linux ARM platform where the EyeVision is available, so that you can do solutions based on that, simply by remote programming. Yes, so for the moment, in this case, to round it up, of course, once again, we could disconnect and run it. Or if you have multiple runtimes and maybe you don't want to use this smart camera, but you want to run parallel multiple independent processes, you can use the local runtime system, which is similar to it. As we saw it, you can then disconnect and the runtime runs. And in this case, in our case, if you want to shut down the local system, you cannot unpower it. You have also the option to disconnect, to terminate this runtime. And if you terminate it now, the camera is shut down. And we are back in our main remote programming environment. For the moment, this was the overview about our remote system. Of course, you see you have exactly all the tools, all the debugging tools which you have on the normal EyeVision system. And of course, you have the additional advantage to run it on any system which is connected over a network, mostly Ethernet to the system or directly inside of the system. If you have now some questions, I could answer you the questions. Else I would terminate for today this session. As I mentioned at the very beginning, you will find it the next few days in our YouTube channel. So you can see the complete session once again in YouTube with all the details about the smart camera hardware and how to program it. Feel free to contact us in any time. And yes, I say thank you for attending our webinar, and looking forward to see you soon on one of the next seminars. And bye-bye.